attempt is to come back to the standard questions about what the derivatives say and try to understand better what the second derivative is for. So you perhaps might remember that what we did was that if we have a, say, x and y, and here is y equals fx, so if the function is something like this, then at point like this one, you see that the slope of the tangent lines will be going down, so it's descending. Then there is this one where the graph jumps from one side of the tangent to the other. That's the inflection. Yeah, that's what we called it, inflection point. And then it starts to grow. So starting from there, it grows. And at all other points, the velocity, how quickly it descends or grows, is what we would like to call the curvature. So, but what kind of velocity it is, so let's have a look how to define it more properly. So in the geometric terms, the curvature is rather what we see on the right hand side here, right? So if we have a curve, we want to osculate the curve up to linear precision, so by a line as good as possible, then that's the tangent line, and that's asymptotically as good as the increment, right? And then if we want to do it up to second order, so we've got the opportunity to do it like here. So we can simply say that there will be, just for the point of interest, this one, there will be just one circle, so that if we parameterize the circle and parameterize the graph at the same time, then in the point of contact, it will have the contact of order 2. So it will be asymptotically like the increment squared, right? So the precision. And this is a very good example, so I will not go into detail here, but let's go through a little bit, because this is a nice task to compute what's the diameter, what's the radius of the circle, and this will be called curvature. Because you see, in the point of the inflection, like we were here, in this point, it's clear that the second derivative will simply disappear, right? And so what it means is that the radius of the circle will be infinite, because that's, we can view a line like a center, like a circle with the center in the infinity on the perpendicular line. So that's what we are heading at, and it's quite straightforward, because we just notice that alpha, so the slope, so the alpha is the angle of the derivative. So actually the derivative is the tangent function of alpha, and the same alpha appears here, and the same alpha appears here. That's clear from the picture. And then there is just some, well, maybe a little bit tricky consideration, just thinking about, because we measure the angle by the length of the circle, which is between the two lines giving us the angle, right? So that will be s, the length. And we see that rho, that's the radius of the circle, will be just the derivative of the length by the angle, right? So the bigger it is, yeah, that's because it's just this relation. And then just going a little bit further, so we just write down what I already told, that the tangent is this. And if you well, now I will definitely have a ghost or something on the screen, because you can skip this if it's too complicated, but it's, I hope, for at least some of you, nice. So let's just look a little bit. So if we differentiate this again, so on the left hand side we differentiate the tangent and we get this, and on the right hand side there will be a derivative, right? So it's just the differential of alpha of the left hand side will be 1 over cosine square d alpha, and on the right hand side we have the second derivative times dx, right, because it's the derivative of the first derivative. And if we just put this equality there, which is obvious, it's just from, well, just you here, if you put it to the common denominator, cosine square, so upstairs you get cosine square plus sine square, so it's 1, so it's okay. It's like here, and you see that that will be exactly, well, this is the derivative, so it's just this, right? So out of that we get that if we differentiate x, so that's our variable with respect to alpha, we get this side, this thing. Whereas now we want to compute the rho, which is ds over the alpha, right? But we know what the ds over dx is, and we know what dx over the alpha is, so we can put it together by the chain rule, and what we get is the final formula saying this, and therefore the curvature will be the reciprocal value, and the reciprocal value, it's actually, you see exactly what it is. This is the second derivative, and downstairs what you see is the length of the tangent vector to the graph of the curve, so the velocity vector. If you parameterize the graph by x, then the velocity will be just this, so that will be the second component. So this is the length of the velocity vector, and so what you see is just the square root of the length, so the square root of sum of squares will be just the length, and it's the third power of the length. So it's just the curvature has been computed now as the second derivative divided by the third power of the length of the velocity vector. So that's a very straightforward, nice thing, and it also shows the geometric role of the second derivative already formulated in terms of what it does with the curve, which is graph of a function, right? So you see that if the second derivative is 0, so the radius is infinity, so it's just what we expected. On the contrary, if we are in a critical point, so if the first derivative is 0, then you see it's just the second derivative which gives us the curvature. So that's it. But now, of course, this cannot be satisfactory, right? Because imagine we just have something like a plane without coordinates, and there will be a curve like this, and we want to see what is the curvature of the curve at this point. So of course what we can do is we simply choose some coordinates and say that we just have the coordinates like that, and piecewise we simply get it as a graph then. But how do we know that it will give us always the same? So what about if our computation depended on how we choose the coordinates? And that's something we don't want to. So we rather should deal with the situation where we would be, say, either in the plane or better in the space. So in the space we would have again a curve here, say something like this, could be curved in any way, and then we would like to understand this curve, so that would be something like ct, and the parameter parameterizing the curve is somewhere else. So here is the t, here I have x, y, and z. So actually the curve ct is for me rather something like xt, yt, and zt. So it's 3 independent functions, right? But again, I would like to see the things appearing and working without dependence on the chosen coordinates. So how to do that? So we should like to introduce something which is called vector differential calculus. So we can have simply a function which is valued in a Euclidean space. So we already know what a Euclidean space is, so we know what the length would be, etc. And so you can imagine that whatever we did with the definitions like continuity or derivative or and so on, we can do it for the vector valued function. So let's stick to either the values are 2-dimensional or 3-dimensional, and we can easily just get the coordinates. Why not? And so what we get is just, there will be the curve, which I call it here the RT, not CT. So it's because this is the radius, so radius vector from the beginning, which I measure, right? So I run on a path through R3, and I've got the radius from the 0 to every point in time t. So that's what's happening. And in the plane, I have the 2 coordinates. In the space, I would have 3 coordinates if I choose the orthonormal basis there, which is something I do. And now, of course, if I want to differentiate, it will be differentiated component-wise, because it's very straightforward to see that all our definitions of the limits, both for continuity or for derivative or whatever, will always work component-wise. So the vector valued function will have a limit or a derivative if and only if each of the components has got it, and then this is the result, right? So we can simply write a differential, which is again something 3-dimensional vector times dt, right? So it's the linearization of the R. Everything works as it did before, so there is absolutely no problem. But now we should learn how to generalize our chain rules and things like that, and that's what I'm doing now. So I want to differentiate composite maps. So you see, what we shall need to compute the curvature and define it properly is I have a curve in Rn, and let's assume that I prolong this curve with some linear map. So I have a linear map between 2 Euclidean spaces. I currently don't need its Euclidean, just any vector spaces, why not? And I just compose psi with R. So and now I want to differentiate. So that's easy. So it's just straightforward. It's again, it will be done component wise, but the point is that the linear mapping can be put outside and you only differentiate. So you simply apply the linear map to the derivatives of the curve, to the vector of velocities of your path, and you will get exactly what is the derivative of the composition. And the computation is straightforward, because if you write it down in coordinates, so it will be such an expression, and the expression just component wise is exactly what we need, right? So all the a's are constants, so the derivative has got the property that derivative of sum is sum of derivatives, so it's just obvious that it will be exactly what I claimed. The second claim is that if I have a k-linear form instead of linear mapping, that's more complicated, because it's something like a product, right? So multilinear form simply takes many things and multiplies them together. So it's exactly like a product, and it's true that there will be again the slightly generalized Leibniz rule saying that if I take the function phi, which will be a composition of the k form with k curves, so I got R1 is a curve in Rn, and so on up to Rk is a curve in Rn. So if I take all the curves and apply my k-linear form, then I get exactly what you would perhaps expect from the Leibniz rule. So I simply always plug in the derivative of one of them and leave all the rest untouched. And this is in the form, right? And I have to do it with all the coordinates one by one, so it will have k terms in the sum. And again, this is absolutely straightforward, because you know that all the k forms are simply given in such a way in coordinates. And now we apply the regular Leibniz rule for each of the terms separately, and you get there. So that's it. And of course, I mean, if I do the same as the previous one, but it won't be a k-linear form, but the values will be in some other vector space, then component wise it will be this, and therefore it will hold true as well. So that's the sort of beginning of the vector calculus. But this is very nice, because now we can employ this dealing with the scalar product, right? So imagine we got two vectors depending on time, so actually two curves in a space, and we shall well, so unfortunately I didn't tell in the other course yet what the vector product is. We shall come to that later, but in R3 you can imagine what it is. So in R3 the vector product works in such a way that you simply take your two vectors u and v, and in some sense what you do is you take the vector product will be a vector which is perpendicular to both of them, and the size of the vector will be, so it's v times u, and the size of the vector will be related to the area, so it will be like the area of the triangle. Well, actually the area of the parallelogram. So for example, if you take E1 and E2, the two standard vectors, then E3 equals, well, as I drew it this way, so it would be E2 times E1. That's a matter of orientation, because you want to have a positive orientation, right? So if we differentiate scalar product of our two curves, then we simply have this rule. So we differentiate one and leave the other, differentiate the other, leave the first. And if we differentiate the vector product, it's again the same, right? Because the vector product is a vector valued antisymmetric bilinear form. So this is the thing. And now, having this very little stuff told or already from the vector calculus, we can use it to tell what the curvature of the curve would be, right? So for each curve in a Euclidean space, so let's see, we have got a Euclidean space E1, E2, E3, and let's say that we shall have a curve there, something like this, and we shall parameterize the curve by length, because we know what the length is, yeah? So the length of the curve is in Euclidean space. Actually, we shall compute it by integration soon, so in the next weeks, but we can imagine what the length is, so in R3. And now what we do is we know that if we parameterize it by length, then the velocity vector will be always of size 1, and therefore the scalar product of the r dash with itself is simply 1 for all s. And then when we differentiate it again, we get 2 times, because the scalar product is symmetric, so we would have to differentiate the first one and leave the other untouched, and then leave the first untouched, differentiate the other. But this is twice the same thing, so 0 will be 2 times this. And this shows you that the second derivative, the vector valued second derivative of our curve, is always perpendicular to the first derivative. So this is what's told here, and that's the first thing what we do when building the so-called Frenet frame. So we have the RT, you see, I fix a point here, and I have the velocity vector, that's this one, and I have got the perpendicular second vector. And then there is the vector product of those two, which will be perpendicular to those, and this is the so-called binormal vector, right? So we have always a frame of 3 vectors at each point, which are naturally given by the parameterization by length. So that's very good, right? So the plane is the plane which is which is orthogonal to r dash. So both the second derivative of r, which is the normal, and the binormal is in this plane. Right, now if the second derivative is non-zero, then we can normalize it, right? So there will be a normalized second derivative vector, and of course the multiple we need to tell what was the original second derivative is well defined, and that's what we call curvature. So that's the curvature of our curve RS. Right. And if the second derivative is 0, then we say that the curvature is 0. Right, and what can we do more? We can now look at the binormal, which is the vector product, as I told. Well, just to normalize it, we take the derivative, which is of length 1. We take the normalized normal, the principal normal, which is the NS defined right now, and that's what we call the binormal of RS. And now there is a very straightforward direct computation that the scalar product of B with R dash is 0, right? Because it's all the time 0, it's all the time perpendicular to each other. I already explained that. So if we differentiate 0, constant 0, then we get again 0, so it's okay. And we also know what it does. So it's the derivative of B, untouched R differentiated, and the untouched B and R differentiated. And this is possibly expressed via the curvature, right? Because here the curvature is the multiple of the normalized principal normal. And so you see that the derivatives of the binormal and the velocity is also perpendicular, right? Right, and now it means that the derivative of B must be a multiple of the normalized normal, right? So the principal normal of the curve. And this is up to sign called tau, and it's called torsion. So each curve in R3 has got torsion and curvature. And as you could imagine, now if you compute again the derivative of the principal normal, you find out that it's always expressed as the torsion times the binormal minus curvature times the velocity. So summarizing all this together, we have this sort of Frenet-Serre formulae, and you see that the derivative, so the velocity vector, is the curvature times the principal normal. The derivative of the principal normal is expressed via torsion times the binormal minus curvature times the velocity, and the derivative of the binormal is minus torsion times eta s. And well, so far it's not so exciting, is it? At least not so exciting if you don't know what it tells. But actually it's absolutely fascinating, because there is this theorem which I will not prove, but I can at least state it. And this says that if you forget about the coordinates and you simply take two curves in R3, so imagine it would be just, say, metal wires, right? Two curves, one here, one here. So for each of them I can compute, well, I can parameterize them by length, both of them, and for each of them I can decide what's my origin in the curve, so where the time 0 would be, and I compute in any normal coordinates I wish, I compute their curvature and torsion. And then the theorem says that there is a Euclidean transformation, so it means some mapping which keeps the distances and is just some Euclidean movement, which is built of rotations, reflections, and translations, exactly as we heard it already in the plane, and we shall come to that back in the end of the semester, so that it maps one of the curves onto the other up to the shift of the origin, right? So we simply can be forced to sort of reparameterize the curve where the beginning is, but otherwise it's completely fixed just by the curvature and torsion. And of course we started with plane curves, just the graphs, right? The graphs of functions, and we can apply this, and a curve is a plane curve if and only if the torsion is permanently zero, constant zero. So for plane curves, of course, the torsion is not there at all, and so also the binormal is simply all the time the same, right? So you have a curve in a plane and you take the coordinates so that the binormal will be all the time the perpendicular one. So that's it. And then if you are very adventurous, so you see another ghost here. Of course we are interested whether the computation of curvature, which was given by the second derivative of a function, is the same as the curvature we get from this, and the answer is yes, as you would expect, but the computation is quite unpleasant, so I would have troubles to understand what I wrote, and I hope it's okay. But of course you are invited to go through and try to check that I wrote it correctly, and if you find it's not correct, please let me know. So thanks.